learning about Simulink at the end of last semester, but at the time we didn't have a full license, so we couldn't get access to the full function blocks that are required in power system modeling. But we resolved this issue at the beginning of this semester and have been working smoothly since. So our initial goal for Simulink was that we wanted it to simulate energy generation from renewable resources, as well as model the energy distribution throughout the Kingdom of Tonga. But the more we worked in this model, it became apparent that this is going to be very complex. To model grid integration in Simulink requires an intensive background in power electronics, as well as a high level of proficiency in Simulink, which none of the team members had. But luckily for us, we were introduced to DEW, which is software used solely for energy distribution, and Paul will talk more about this in a few minutes. But with DEW, we were able to reduce the scope of our Simulink model to just simulate the energy generation side. And as an update, we finished with the solar model and the wind models, and hope to finish with the wave model in the upcoming weeks. Within our models, we'll be able to see the energy generation from renewable resources for an hourly segment throughout the year. This will be very helpful because we'll see the energy fluctuation and can tell where the energy shortages will be, and also determine the usable capacity that will need to be available. One important limitation to note from our model right now is that it does not account for any storage system. This means that we're assuming that all the energy generated from the sources are being inputted directly into the grid, which in reality is not, sometimes might not be possible if the energy generated exceeds the capacity of the grid. So next, I'll talk about the three models that we currently have. Here we have the solar model, and the main inputs of this model are Tonga solar radiance data and manufacturer PV cell specs. One of these specs includes the voltage, and the voltage is a property of whichever PV cell we choose to model. In our case, we're modeling the SunPower 225 solar panel. And using this equation, in our model, we were able to determine the current output from the PV cell based off of the solar radiance data. And as you recall, power is defined as voltage times current. So with these two values, we can determine the output, the energy output from the PV cell in the units of watts per area of the cell. And here we have the wind model. The wind model consists of 4 if statements that generate electricity based on wind speed. The relationship between wind speed and power generation is given by the wind turbine's power curve. The power curve shown here is the power curve for the V82 1.65 megawatt turbine. So basically each if statement corresponds to a portion of the power curve. And so for example, this top if statement states that if the wind speed is below 4 meters per second, there would be no power generation. And the block below that corresponds to the linear sloping line on the power curve with the generated energy proportional to what that line says. And then the third block states when the maximum rated power will be generated from, which is from 12 to 22 meters per second. And then the final block incorporates the cutoff speed which states when the wind tower turbine will turn off if the wind speed exceeds 22 meters per second. And finally, we have the wave model. And this model basically consists of a simplified energy generating equation for a point source floating device, which is what the Thalamus system is. The inputs in this equation are mean wave height and mean wave period. We have these data in a monthly basis right now from a study that was conducted off of the coast of Tonga, Part3 in the 1990s. But we hope to find hourly data for this in the future that correspond with the solar and wind models we have right now. So from the model, here's what we get. So this is hard to see because it's shown over 8,000 data points for each hour in the year, with the top being the solar output and the bottom being the wind output. To better see the fluctuation in the energy generation, we selected a 24-hour period in a day in October, with the blue line being the solar generation and the red line being the wind. And as expected from the solar generation, for example, we see that there would be no generation at night. And in our graph, it would be from about midnight to 6 a.m. and then also from probably 10 p.m. to midnight. And with the energy output from Simulink, we'll use them as inputs in the DEW system. And with that, I'll hand it off to Paul.
Thanks, Jen. So as Din mentioned, we decided against using Simulink to model the grid because it requires knowledge about power electronics that we don't have. So fortunately, we learned about another software that is specifically designed for grid modeling. And this software is developed by a firm based here in Blacksburg called Electrical Distribution Design, or EDD for short. And their goal is to partner with small and large utility companies to provide modeling solutions that address the industry's most demanding issues. So basically, what that means is they create software that can model grids. And so the heart and soul of EDD is Distribution Engineering Workstation, or DEW, as Dan has mentioned. And this program enables the construction of a complete working model for the entire power grid, from the transmission level through primary and secondary distribution networks. Basically what that means is DEW can model a complete grid down to every single distribution line and transformer. And so REEF has contacts with EDD. Dr. Robert Broadwater is on faculty here in the Electrical Engineering Department. He's also the Chief Technology Officer at EDD. And he has provided us with 10 user licenses for DEW. And then Jason Jun is a PhD student studying under Dr. Broadwater. And Jeremy White is one of his master's students, and he's an EDD software developer. And so these two men have been working with us in understanding how to use DEW and in developing a model for our specific system. As I said before, DEW is a very powerful software. And as I said, it can model an entire grid down to every single distribution line and transformer. It can accept power data and analyze its distribution across the entire grid. And this will become a little more clear as I move to the next slide. It can accept load data, which is important to know which portions of the grid require more or less power, depending on how many houses in the area or manufacturing facilities that may require excessive power. And then it can show the results of a power failure. So for example, if a tree falls on a line, you can basically turn that line off and it'll model how the grid will respond to such a loss in a distribution line. And as Dan said, we will input the hourly power output we get from Simulink. We'll put that into DEW, and then it can analyze its distribution across the entire grid. Now here's a sample I put together. What you see here is a simple layout of or a Google Earth image of part of Tonga, and I've pretty much laid out a simple grid. Each of the blue lines represents a transmission line, and as you can see, I've sort of followed the main roads. This right here represents where we inject power into the grid, and each of these red icons represents a load. And so as you can see, I've sort of put a load bus and where I see sort of a large group of residences or manufacturing facilities. Now, we are experiencing somewhat of a roadblock. It would be nice to know the exact layout of the currently existing grid. However, we haven't been able to get that. I sent an email in February to the CEO of Tonga Power Limited, which is the utility on Tonga, and I have yet to hear back from him. I requested from information on the existing grid there, but there are two possible reasons why he hasn't contacted me. First, they may not really know a whole lot about the grid. Typically, grids are constructed over a course of many years and sometimes by different contractors, and so their methods might be different, so important to have a whole lot of information. Secondly, it may be against the policies of many utility providers to provide such information to groups like us. So I highly doubt that we're going to be able to really get detailed information on the grid. So like I said, we're really going to follow the main roads and make an approximation as to what the grid looks like. So with that, I'll let Jack wrap it up and tell us about our future plans.
Thank you, Paul. So one of the first things I'd like to point out is a screenshot of a Gantt chart that we have included here. And I know you probably can't read anything specific off of here, but I just wanted to illustrate the point that we have kept a very detailed schedule throughout the year, and we have three important upcoming deliverables that I'd like to highlight for you. The first of which is our business plan, which we hope to have wrapped up by April 5th. And then shortly thereafter, we hope to wrap up our engineering plan and detailed simulation and have pretty much our entire package complete by April 24th, which will give us a little bit of time at the end of the semester to put the finishing touches on our project. Now, as our project has gone on, our goals have transformed a little bit. And we went through a reorganization not too long ago to more effectively address how we could apply our efforts towards meeting those goals. So here's a flowchart of our old organization. We had such sub-teams as concepts and system integration, energy resources, and so on. And as I've mentioned, some of our efforts got sort of outdated as our project went on. So site identification, for example, once we selected Tonga as the site that we wanted to design our system for, they no longer had any function. So we reorganized in such a way that we have a manager and team logistics team at the top. They maintain that Gantt chart and just kind of keep us on schedule, coordinate our efforts. And below them we've split the rest of the team's efforts towards addressing the three deliverables of the engineering plan, the business plan, and the simulation. Those are further broken down. As you can see here, the engineering plan is broken down according to the components of our system architecture: solar, wind, tidal, and storage. And simulation is similarly broken down in terms of the two simulation softwares that we will be using. So our end-of-year goal, as we've kind of mentioned throughout the majority of this presentation, will consist of our three main deliverables of the engineering plan, the business plan, and the simulation. And these three things will combine to form a package that will serve as the result of our whole project. And although our project will be ending here in a couple months in May, we hope to pass it along for further development. The first way we hope to do that is by having it serve as a proposal to address the energy needs outlined in the Tonga Energy Roadmap. And we also hope to have another similar design team take over for us next year. And we'll pass along our methodology to them and let them approve upon it. And they will actually be most likely working with a NASA facility on Wallops Island, which is here off the coast of Virginia. And we've actually already established contact with them, and they've expressed interest in working on a project like this. So that actually concludes our presentation, and with that we'd like to open it up for questions.